Okay, guys. So I'll be beginning with the things. In the previous class, I have mentioned about what is a tree is and how it is different from linked list or stack or queues. When I take up linked list or arrays or stack or queues, all those things are nothing but linear data structures. But now what I'm speaking about is hierarchical data structure, which is called as a tree. How this Why these trees are required, first of all. Okay. Guys, please answer to me from your end by telling yes or no. Have you seen the arrangement of folders or files in Windows? Have you seen the folder arrangement in Windows? Type yes, no. If you know yes, type yes, otherwise no. Quickly. Okay, now you can see, thank you for your answers. Now you can see in such kind of applications, it is main mandatory that I have to go for what is called as hierarchical structure. Some of the applications they require or they prompt us to go for what is nothing but hierarchical arrangement of the elements. It means what? After finding the value of A, only then I can find the value of B. So they are interdependent. If there is something called as interdependency in the operations or interdependency in the kind of the values that I'm using, then definitely I have to go for what is called as hierarchical structure. This has to happen first, then the second, then the third, like that. So in such cases, trees are to be used. The second reason, let me just run the slide. The second reason why we require the trees. Uh, when I take up when I take up a binary search tree, okay, you will get to know about it in my next class, tomorrow's class. There are trees called as binary search trees, which ensures the ordering of the nodes. When the elements or the nodes are arranged in a proper order, searching would become much convenient. But it may not be quicker than arrays. I think Praveen had told me the same thing when I was teaching linked list. Arrays is fastest searching because it talks about index. Through the index, you can search very quickly. But storage of the elements, if there are hundreds of thousands of growing of elements is there, then arrays is not preferred. If there is fixed number of elements always, then arrays are the most preferred data structures. Otherwise, if there is growing and shrinking of the data elements, then I'll go for either linked list or the trees. So if I arrange the elements in an ordered manner, searching becomes much easy, much convenient. Okay, with that reason, the trees are being introduced. Then, third reason, trees provide moderate insertion deletion. It is not so slower, it is not so faster. Okay, when I take up arrays with insertion, at the rate and goes on inserting. Simple insertion, simple deletion. If I take up queues. But when I take up insertion and deletion in between, then trees or linked list would lead to what is called as a moderate level of insertion or deletion procedure followed. Then, like the linked list, trees do not have an upper limit of number of nodes. Number of nodes is not fixed. This is the only advantage of these kind of data structures over arrays. Due to these reasons, we go for another data structure called as trees. Now, there are different types of trees. When I take up the types of the trees to be done based on the number of nodes in each level of the hierarchy. What is this level of a tree? See, you can just please don't look at the left hand side. Look at the right hand side. I can just show you one example of tree where the nodes are arranged in different hierarchies. When you take up at every level, if I tell the maximum number of nodes, if the maximum number of nodes in the whole of the tree at every level is equal to 2, is equal to 2, then I call it as a binary tree. I'll repeat again. I'll just go back. Okay. Based on the number of nodes in each level of the hierarchy, the type is decided. Now, you just assume that I have a tree structure arranged like this. I have a tree structure arranged like this. Okay. There are nodes arranged like this. So at every level, I will consider this as level 0, this as level 1, this as level 2. When I consider every level, each and every level in the whole of the tree, in each and every level, what is the maximum number of nodes at each level? That decides the kind of the tree. Look at this diagram. In each level at max, I will be showing 2 nodes per root node. Under each node, there are exactly 2 nodes. You can just see under this node is there, this node is there. Under this node is there, this node is there. So at every level, every parent is having 2 children. Such a kind of tree is called as binary tree, where at every level, maximum number of nodes per root node is equal to 2. Then it is called as binary tree. If there are, sorry, it is not 2 nodes. If there are 3 nodes at every level, then I call it as ternary tree. Similarly, if there are n nodes at every level, then I call it as n-ary tree. Okay. So type of the tree is decided based on the level at which the number of nodes are available. Now, first thing that I will take is the binary tree. A binary tree is a tree whose elements have at most 2 children is called as a binary tree. It's a tree where every node has at most 2 children. At most means at max 2 children, not more than that. It doesn't allow 3 nodes at any point in time. Such a tree is called as a binary tree. Okay. Now, I will be drawing few of the trees for you. You have to tell me what is the type of the tree. Okay. Guys, can you do this? Can you do this? I'll be drawing the trees for you. Okay. You have to tell me what is the type of the tree that I have drawn. Okay. I will be representing a dot for a node. Okay. And this represents the edge of the tree. Now, you tell me what is the type of the tree that I am drawing. Okay, can anybody tell me what is the type of the tree here that I have drawn? Yes, it's a ternary tree. Now the next one. Now tell me, what is the type of the tree here? Binary. Why it is binary? Though there are only 2 edges in the level 2, but you can see the first node is having 2 children. Okay, based on that you have to decide. Okay, now tell me, what is the type of the tree? Quadary. It is called as quadary or fourary. Okay, so based on the maximum number of nodes that are available in the tree, the type of the tree is decided. Now, if a tree in all the levels has at most 2 children for every node, then it is called as a binary tree. Now, how do I represent this binary tree? Let me just skip this and restart. How do you represent this binary tree? Node of a binary tree. Every element will have 3 parts in it. Similar to double-ended or doubly linked list, we have 3 parts. Okay. One is the info part. At the center, I call it as the info part. At the left side, I call it as left. At the right side, I call it as a right. Okay. So left contains the pointer to the left child, right contains the pointer to the right child. This is how a node of a tree looks like. If a node is the only node available in the tree, then I call it as left equal to null, right is equal to null. Okay, if both left and right are null, it indicates that this is the only node that is available in the binary tree. Now, before we proceed ahead with the things that we need to do in the implementation of the trees, we go through something called as tree related terminologies. Okay, now tell me, what is the kind of the tree I have drawn here? What is the type of the tree that I have drawn? Yes, it is ternary tree. Now in this tree, which is a root node? A is the root node. So can I call a node which is having in degree equal to 0? I'll repeat. A node in a tree which has in degree equal to 0. What is this in degree? What is this out degree speaking about? I'm directly going to the fourth terminology that I have listed. In degree indicates the number of edges that are going towards the node. They are called as in degrees. The total number of edges that are going away from a node, that are called as out degree. Okay. Degree of a node is the sum total of in degree and the out degree. Whether you have come across these terminologies in graph theory in discrete structures, please let me know from your end. Have you come across this in discrete structures? Yes. So it becomes much easier to understand that. Now with reference to this in degree and out degree, I will try to explain the things that are available other than the degrees. Okay. Now root node is a node which has in degree equal to 0, or root node is a node from where the tree starts growing. Root node is the base node from where the tree starts, or the node at level 0. The node at level 0 in a tree is called as root node. So many definitions are there. Don't write a bookish definition, please. You, if it is asked, explain the following, explain these things with reference to a tree, then please don't write bookish language definitions. Okay? Write the things that you have understood. Now, what is a root node? If I ask, root node is a node which is at level 0 of a tree. Root node is a node which is having in degree is equal to 0. Okay, root node is the starting node of any binary tree or any tree. Fine. So, next. What are leaves? The leaves are the nodes which do not have any outgoing edges, or the nodes without degree is equal to 0 are called as leaves. The nodes who do not have any children are called as leaves. So can you find out which are the leaf nodes available in the tree that is being depicted here? Tell me whether B is a root node. Yes or no, you have to tell me. Whether B is a root node? No. Why it is not a root node? Because it has children. Okay. Whether D is a root node? D is a root node? Sorry, whether D is a leaf node? Yes. Whether E is a leaf node? Capital E, whether it is a leaf node? No. So the leaf nodes in the depicted picture are D, I, J, F, K, H. I'll repeat. D, I, J, F, K, H. I'll always move from left to right. It becomes much convenient to write the things. You'll not miss anything if you start in the orderly manner. Okay. So if I give you a diagram and ask you to identify the following: root, leaves, degree of node B. Can you tell me what is the total degree of node B? It's 4. How? In degree is 1, out degree is 3. Okay, 3 plus 1 is 4. Now if I ask you, what is the out degree of E, capital E? 2. Why it is? Because it has 2 children. Yeah. So now tell me, which is the parent of J? which is the parent node of J. E, which is a parent node of EF. Okay. What all are the children of C? G and H. Correct. Now, if I ask you, tell me the siblings of F. I'll repeat. When I tell sibling, siblings are those with common parent. The nodes with common parent. When I tell siblings of F's parent is B. Now you have to identify who all are the other children of B other than F. D and E along with F are having the common parent B. So D and E are the siblings of F. Siblings are the nodes which are having common parent. Okay, tell me which is the sibling of C? B, correct. Which is the sibling of K? No one. No siblings are there. Which is the sibling of J? I, correct. So all of you know about it. Well and good. Now, the last one. Internal nodes and the external nodes. I'll explain what are internal nodes and what are external nodes. Then you will be able to identify them. The nodes which are either root or leaf nodes are considered to be external nodes. The nodes which are either root or leaf nodes, they are considered as external nodes. Leaving root and leaf nodes, whatever left out, are internal nodes. I'll repeat again. Root and leaf nodes together constitute for external nodes. Leaving leaf node and the root node, whatever they are left out, they are called as internal nodes. It means what? Internal nodes must have at least one or the other children. Okay, they are termed as internal nodes. So tell me which are the external nodes in the tree that I have shown. I'll just discard the things and I will restart. Okay, which are the external nodes? Can I take up A? A being the root, I'll consider it as external node. D, I, J, F, K, H and A together are considered as external nodes. Now, whatever that I have marked, they are considered as external nodes. Leaving them, what all are there? B, E, G and C are termed as internal nodes. Any doubts here? Any doubts at this point? Quickly. These all are very simple things. That's why I'm running like anything. No doubts? Okay. Now tell me, if I take up A as a root, who all are the ancestors of A? Who all are the ancestors of A? Is there any ancestor of A? No ancestor. Ancestors are nothing but all the nodes in the path from a node to that particular node, root to that particular node, of all the nodes who come in the path from the root to the node X. All the nodes in the way are called as the ancestors of the node X. Okay. Now if I take up E as the node, who all are the ancestors of E? B and A. All the nodes starting from root till node X are termed as the ancestors of node X. Now predecessors. Who all are the predecessors of A? If I take predecessors of A, every other node other than predecessor, okay, followers or successors, I tell. Who all are the successors of A? If I ask successors of A, all the nodes except A are termed as successors of node A. Okay. Now, can I ask you who all are the successors of G? It's only K, correct? So the all the nodes that are below the node X in the path till the leaf node, they are termed as the successors of that particular node. Whether these terminologies are okay for you. Now, if I take up the same tree mentioned with levels, you can just see the levels I have marked. Okay. The first level of any tree is nothing but level 0. Who stays in level 0? Level 0 always has a root node of the tree. Then the all other nodes are arranged in the increasing levels in such a manner that the maximum number of nodes that are allotted per level is based on the kind of the tree. Now, level 1, which all are the nodes available in level 2? If I ask you, I'll just go back. Which all are the nodes available at level 2? Or level 2 nodes, if I ask you. D, E, F, G, H. Okay, they are in level 2. Which all are the nodes available in level 3? I, J and K. What is the total level of the tree? When I ask you total level of the tree, I'm talking about 0, 1, 2, 3. 3 is the last level of the tree. So the level at which all the leaf nodes are ending, that level is termed as the level of the tree. Level of the tree at which all the leaf nodes are ending, the last ever leaf node is ending is 3. If I ask you what is the height of the tree, height of the tree is nothing but level of the tree plus 1. Whatever you have responded, that indicates the height of the tree. So level of the tree plus 1 indicates the height or the depth of the tree. Okay, so for the given diagram, the level of the tree is 3, height or depth of the tree is 4, level plus 1. Are you all okay with this? Can I proceed ahead? I'll repeat again, Praveen. Okay, you have asked me to repeat the things. Level of a tree is the level at which the last leaf node is available. That is considered as a level of the overall tree. The last leaf node in the given tree is at level 3. It means the level of the tree is 3. Whereas the height is always 1 above the level of the tree. That is, level of the tree plus 1 indicates the height or the depth of the tree, because height is always measured in the positive direction, never considered with 0. Whereas level is considered starting from 0th level. That's why level is always height minus 1, or height is always level plus 1, height of the tree. So if I tell A is at level 0, the last leaf node is at level 3, it means level of the tree is 3. You just imagine there is one more node, say L. Now what is the level of the tree? Now it is 4. The level at which the last leaf node is resided, that indicates the level of the tree. What is the height of the tree, including L? 5. Yeah. May I know who is speaking? Yes, Praveen, you have doubt?
Uh, Ma'am, I wanted
Yeah.
to ask what are the examples of internal nodes, ma'am? Whether these are B, E, and GC only, na, ma'am?
We have a B, E, C and G. Yes, you are right, Praveen.
Okay, ma'am. Okay,
Yeah.
thank you, ma'am.
Okay. So can I proceed ahead? Okay, I'll take up now the important part that is called as binary trees. What are binary trees before we proceed ahead? A binary tree is a tree where every node has at the most 2 children. At most, it means every node may have 0, 1 or 2. Now, if I draw a binary tree like this, Is it a binary tree? Yes, of course. It's a binary tree. It's a binary tree, but the root node has exactly one child. Now, if I draw only root, can I call it as a binary tree? Yes, of course. It is the root of the binary tree. It can be either binary, it can be ternary, it can be quaternary, it can be n-ary. I don't know. But when I'm talking only in terms of binary tree, I call it as a binary tree. Okay. Now, if I draw like this is a binary tree because a root node is having exactly two children. With this background, I'll just go through few of the important subtypes of binary trees. Okay, let me go to the first one. I call something called as strictly binary tree. Let me just discard the things that I have written and then I will begin again. Okay, now I have three very important categories of binary trees. Guys, you please pay attention in just having the distinction between these categories. First thing that I call as strictly binary tree. What is this strictly binary tree? I'll draw a diagram for you. Okay. I'll draw a diagram, binary tree diagram. You please notice the thing that I'm doing. Okay. Now I'll draw one more diagram. I'll draw one more diagram. Please consider the vertex that I have drawn as the node. Okay. You can just see the three diagrams that I have drawn and what is so important that you have to notice. You can unmute and tell me. In all the three diagrams, there is one commonality. What is that commonality factor? All three are common. They have, yes, every parent at any point in time have exactly or strictly two children. Now, if I draw something like this, I never call it a strictly binary tree. A strictly binary tree is a binary tree in which every node has exactly two children. It cannot either it has zero children or two children. So tell me, in this, which is a node that is having zero children? Look at this, root has two children. This node has two children. This node has zero children. This node has zero. This node has zero children. So every node in the whole of the tree either has two children or zero children. Then I call it a strictly binary tree. Okay, I'll show the diagrams for you. Okay, this is an expression tree that I have drawn. You will not, don't worry about this. I will be taking up when I cover binary search tree. Okay, now you can see in both the diagrams, in the diagrams that I have drawn, in all the diagrams, what is that you have to observe is, very importantly, every node in the whole of the tree have either zero or two children. None of the node is having exactly one children or one child. I call it as strictly binary tree. Second, I talk about what is called as complete binary tree. Complete binary tree tells me at a level of the tree, at any level of the tree, all the children must be filled. It means what? At any level you take, there has to be 2 to the power L number of nodes. I'll repeat again. What is level? L, if I consider as the level of that at that moment. Every level must have 2 to the power L nodes. If I draw a diagram for you, this is a root node. How many nodes in level 0? Level 0, 2 to the power 0 is equal to 1. Now, if I draw next level, level 1, at level 0, 2 to the power 0 is equal to 1. Now, at level 1, 2 to the power 1 is equal to 2. At level 2, can I call this as a complete binary tree now? Please let me know from your end. Can I call it as complete binary tree? What is level 2? What is the level at this point? 2. Level is 2. 2 to the power 2 is equal to 4. I must have 4 nodes. And since I'm talking about binary tree, every node must have maximum 2 children, not more than that. So now I can call this whole tree that I have drawn as complete binary tree. Now tell me, what is the category of the tree that I have drawn? What is this called? Can I call it as complete binary tree? The diagram which I have drawn. Yes, it is strictly binary tree. Very good. It is called as strictly binary tree, but not complete binary tree. A complete binary tree can be called as a strictly binary tree, but not vice versa. Not vice versa. Now, I will draw one more diagram for you. Tell me, what is the category of binary tree that I have drawn? Is it complete? Is it complete? Quickly answer to me. Is it complete? No. Is it strictly binary tree? Is it strictly binary tree? No. I call such a kind of tree as almost complete binary tree. I'll call such a kind of tree as almost complete binary tree. So how do you define this? A tree where a tree of level L have nodes in such a manner that tree up to L minus 1 level is complete, but there are less number of nodes at level L. I'll repeat again. A tree where the total number of nodes up to level L minus 1 is complete, but at level L the nodes are still incomplete. Such a tree is called as almost complete binary tree. Two things are there. Two properties. First property, the tree up to level L must be complete and the nodes must be filled from left to right. Filled from left to right at level L. I will repeat again two properties of almost complete binary tree. A tree where the nodes at level L minus 1 up to level L minus 1 is complete binary tree. This is first property. Second property, at level L, the nodes are filled from left to right. Then I call it as almost complete binary tree. Let me draw the diagram for you. Then you'll understand it. Okay. Now let me keep this blank for a while. Just pay attention. Okay. What is the kind of the tree that I have drawn? Fast you must be now. It's complete. Now tell me. Strictly. Okay. Now tell me. It's almost complete. Now if I draw like this, please pay attention guys. This is the variation you must understand. Now tell me, what is this tree called? Can I call it as complete binary tree? No. Can I call it as strictly binary tree? No. Can I call it as almost complete binary tree? No. Why it is not almost complete? It is just because every node has two nodes, two children. That is definitely 0 or 2 children, 0, 1 or 2 children. Definitely it is correct. But the elements are not from left to right. Second property, that indicates strictly binary, sorry, almost complete binary tree. Up to level L minus 1 it is complete. But how the elements are filled in level L? They are not from left to right. Directly it has gone into right side. So I cannot call it as almost complete binary tree. Then what is the name of this? It is simply called as a binary tree. It's a binary tree. Okay, let me redraw again. Now you have to quickly tell me the type of the tree that I'm drawing. Okay. And then I will end the class. Okay. Now tell me, what is the type of the tree? Correct, N-ary. But if I talk always in terms of binary tree, what is the type of the tree? I have assumed that binary tree it is. Then what is the type of binary tree it is? I call it as complete binary tree. Complete binary tree of level 0. Please make it a point. A single node in a binary tree indicates a complete binary tree at level 0. Okay, with level 0. Now, what is the type of the tree that I have drawn? Assume I have started with binary trees. What is the type of the tree? Almost complete. You're right. Now, what is the type of the tree? Complete binary tree. Now, what is the type? Complete. Okay, now what is the type? I call it as a binary tree. Don't get confused. If none of the categories match, then I call it a simple binary tree. Okay. Now tell me, what is the type of the tree? Almost complete. It is almost complete. Yes, now complete binary tree. Very nice. Very nice. What is the level of the tree? Please pay attention and answer to this. 2. Okay. What is the height of the tree? 3. Correct. How many leaf nodes are there? Okay. Now, what is the type of the tree that I have drawn? Strictly binary tree. It is strictly binary tree. Yes. Yes. Thank God you have understood it. Nice. Okay. Now, the question comes, why do I require this binary tree? Binary tree has a very important property. Every time a node is inserted, the node has to be inserted in such a manner that it should not spoil the property of binary tree. What is the property of the binary tree? Every node must have 0, 1 or 2 children, not more than that. It becomes much convenient to stick on to two number of children at any point in time. Okay, if you imagine every node has 4 children, so the width of the tree goes on increasing like anything. Width has to be in such a manner that you have to be very intelligent to choose the kind of the tree that you want to work with. The width of the tree increases, the searching becomes so much complicated. Height, if it increases, that never matters. You just have to go on calling recursively until it reaches the leaf node. But if width changes, you have to go on the left and come back to the root, then go to the right, something like that. So number of iterations in searching, if the width of the tree increases, that becomes complicated. That's why most preferred is binary tree. At max, it is ternary tree. Okay, but we go for what is called as binary tree with the special category of binary tree called as binary search tree. What is this binary search tree? I'll just define it and then I will stop. Okay, what is this binary search tree? Binary search tree is a tree in which the elements are arranged in such a manner that every time if you look at the tree, the elements that are lesser than the root node are on its left side or are in the left subtree of that particular node. all the elements that are greater than the root node are available in the right subtree of the root node, or on the right subtree of the node with which you are comparing. Uh, so let me just draw a diagram for you, then you will understand it. Okay, this is the last point I'm making. Okay, I'll just share the screen. And now, if I draw, there is 10, okay, and there is 8, there is 20, 15, there is 5, there is 9, and there is 20. There is, say, 13. Okay, you can just observe this diagram and check. 10 is the root node. 8 lesser than 10, that's why it is on the left hand side. 5 lesser than 8 lesser than 10, that's why it is on the left side of 8. 9 being lesser than 10, it is on the left side of 10, but it is greater than 8, that's why it is on the right side. When I take up 15, 15 is greater than 10, so it comes on the right side. Okay, it comes on the right side. And 13 being greater than 10 comes on the right, but compares it with 15. It being lesser comes to the left. 20 being greater than 10 comes to right, checks with 15. It is greater, so goes on the right hand side. So all the elements are arranged in such a manner that every element is lesser to its, if it is in the left hand side of the node, then it has to be lesser than the root node. If it is on the right hand side, it is greater than the root node. This property, as along with the property of binary tree, if we add this property also, then I call it as a binary search tree. Searching becomes much convenient. For that reason, this kind of thing is done. Okay, so I'll be continuing with this in the next class. Okay, any doubts at this point? Yes, any doubts you have? If no doubts, we will end the class for today and I'll be continuing tomorrow's class. Shall we end the class? Okay, same question. Whether pointer size is architecture dependent. Definitely it is dependent on the architecture on which the C program you are writing. Okay. Shall we end the class? Thank you all.
Thank you.
Okay.